Hello, this is video number 11 on my single variable calculus 2. In this video, we're going to talk about inverse trigonometric functions. So in order to define the inverse of a function, we need the function to be one-to-one. This is something that we talked earlier. None of the trigonometric functions, sine, cosine, tangent, and cotangent are one-to-one. So in order to be able to define their inverses, we have to limit their domains. So let's look at the graph of these functions and then see where these functions are going to be one-to-one. So if you look at the graph of sine starts from the origin, it goes up and it comes back down, and then something similar on the other side. So we have negative pi over 2 here, and pi over 2 here. So in order to make this one-to-one, we would need to look at this piece of the graph or some other piece that is one-to-one. So that's why for sine inverse, the range is negative pi over 2 to pi over 2, and the domain is negative 1 to 1. So when I write down sine inverse of x equals y, it means sine of y equals x with two conditions. First, y is between negative pi over 2 and pi over 2. And second, x is between negative 1 and 1. If we look at the graph of cosine, this one is y equals sine. If we look at the graph of cosine, there is also a natural interval that the function is one-to-one. So graph of cosine is something like this. And the graph is one-to-one from 0 to pi. So in order to define the function, the inverse of this function, we limit the domain to 0 to pi. In other words, when we say cosine inverse of x equals y, that would mean cosine of y equals x. This y is between 0 and pi, and x is between negative 1 and 1. And we can do something similar for tan inverse and cotan inverse. So tan inverse, this is the graph of cosine, and graph of tangent, I'm going to graph it here. So it looks like this. There are asymptotes at pi over 2 and at negative pi over 2. These are our asymptotes. So this piece of it is in fact one-to-one, and there are copies on this side and on this side as well. So I'm not gonna draw those. So if you look at this piece, we can define tan inverse of x to be y when tan of y equals x. Now the value of y would go between negative pi over 2 and pi over 2. Now tangent of pi over 2 and tangent of negative pi over 2 are undefined. That's why y cannot be negative pi over 2 or pi over 2. And x could be any real number. And then we have something similar for cotan inverse. So if we look at the graph of cotan, y equals cotan of x. There is an asymptote at 0. There is an asymptote at pi. At pi over 2, it is 0. When x goes to 0, it goes to infinity from the right, because cotan is cosine over sine, and sine of 0 is 0. So we have 0 at the bottom. And then it goes to negative infinity on this side. So we have a graph that looks like this. This piece of the graph is in fact one-to-one. So we define cotan inverse of x to be y when cotan of y equals x, and value of y is between 0 and pi, and x is any real number. So we're going to look at a couple of examples on this, and then we will talk about how to differentiate these functions. Simplify so there are no trigonometric present. So the first one is cosine of sine inverse of x. So let's call this sine inverse of x angle theta, and let's draw a right triangle whose angle is theta. So this would mean sine of theta is equal to x. X is x over 1. So if I draw a right triangle whose angle, one of the acute angles is theta, then I can say opposite, so this one is opposite, and the bottom one is hypotenuse. Over hypotenuse would have to be x over 1. So we can choose the opposite to be x and the hypotenuse to be 1. Now this missing side, let's call that a, is going to be evaluated using the Pythagorean theorem. So we get a squared equals 1 minus x squared. So that tells us that a is root 1 minus x squared. So this side is root 1 minus x squared. And we are asked to find cosine of this. So cosine of this theta becomes adjacent, which is root 1 minus x squared over 1. So the answer is in fact root 1 minus x squared. So that's cosine of sine inverse of x. The second part is secant of tan inverse. So let's call that theta equals tan inverse of x. We are going to draw a right triangle again with angle theta. So what we know is we know that tangent of theta is equal to x. So opposite is x, adjacent is 1. Hypotenuse would be, let's call that b. B squared is equal to x squared plus 1 squared. So that means b is root x squared plus 1. And we are asked to find secant of that. So secant of theta is hypotenuse over adjacent. So b, which is root x squared plus 1 over 1. So the answer is root x squared plus 1. Okay, so to find the derivative of sine inverse, cosine inverse, tan inverse, and cotangent inverse, we're going to use a formula that we learned before, which is f inverse prime at x is 1 over f prime of f inverse of x. So derivative of sine inverse is 1 over sine prime, sine inverse of x, which is 1 over derivative of sine is cosine, so it's cosine of sine inverse of x. And we just evaluated cosine of sine inverse of x in the first part to be root 1 minus x squared. So we get 1 over root 1 minus x squared. Let's say you want to find the derivative of tan inverse of x. So this would be 1 over derivative of tangent at tan inverse of x. Now we have learned derivative of tangent. Derivative of tangent is secant squared. So this is secant squared of tan inverse of x. And in the example above, I just evaluated secant of tan inverse of x. Let's look at this. We got that secant of tan inverse. So this one is equal to root x squared plus 1. So this would be 1 over root x squared plus 1 squared, which is 1 over x squared plus 1. So this is the derivative of tan inverse. So to summarize, we can say that derivative of sine inverse is 1 over root 1 minus x squared. Derivative of cosine inverse is negative 1 over root 1 minus x squared. Derivative of tan inverse is 1 over 1 plus x squared. And derivative of cotan inverse is negative of derivative of the tan inverse. So these are formulas that you do need to remember. So this is really important formula. So you also need to be able to do the integration of these to get to the left side. And I'll summarize this at the end. Now, if you want to define the inverse of secant and cosecant, you can do something very similar. So in order to define inverse of a function, we need to first find an interval that the function is in fact 1 to 1. And that way we can define the inverse of these functions. So what would be an interval that these functions are 1 to 1? If you look at secant and cosecant, the graph of secant, so we know that cosine looks like this. So graph of secant would be, at this point, it would become infinity. At this point, it's 1. It goes to infinity here, and it goes to infinity here as well. Because when cosine is 0, secant is undefined, so it approaches infinity. So over this interval from negative pi over 2 to pi over 2, secant isn't 1 to 1. So we'll have to look at another piece of the graph. So at this point, it is negative 1. Here we go down. Here we go down as well. So we need to choose one branch from the top part, from the part from negative pi over 2 to pi over 2. So this one is y equals secant of x. And one piece from the bottom one. So which piece do we choose? Well, because of an absolute value that appears in the formulas, the best choice would be this piece and this piece. So this one is pi, this one is 3 pi over 2. So I have summarized that in this table. So secant inverse of x is equal to y. X is between negative infinity to negative 1 and 1 to infinity. Y is either between 0 and pi over 2 or between pi and 3 pi over 2. For cosecant inverse of x is y. X is between negative infinity and negative 1 or between 1 and infinity, and y is in the same range except that it cannot be 0, but it can be pi over 2. It cannot be pi, but it can be 3 pi over 2. So let's look at a couple of examples, and then we'll do derivatives of secant inverse and cosecant inverse. So we want to simplify each of the following so that there are no trigonometric functions. So let's set secant inverse of negative 2 to be theta. So that tells us that secant of theta is equal to negative 2. So we need the secant to be a negative number. Well, secant inverse of negative 2 would be either in the first quadrant or in the third quadrant. But secant is negative, so it would have to be in this quadrant. So let's first figure out when secant is 2. So let's look at an angle whose secant is 2, and then let's figure out what it should be. So I have this angle. Let's call that alpha. That secant of alpha is 2. So that would be something in the first quadrant, and then we are going to add pi to go to the third quadrant. So secant equals 2 means hypotenuse over adjacent would have to be 2. We can find the third side of this right triangle by Pythagorean theorem. So square root of 4 minus 1, so root 3. This one is a 30, 60, 90 triangle. So that tells us that alpha is 60 degrees or pi over 3. And of course, in calculus, we always use radians. So the angle is pi over 3. So that tells us that secant inverse of negative 2 would have to be pi plus pi over 3. So the answer to this part is 4 pi over 3. So that is part A. Part B is asking us to find tangent of secant inverse. So how do we find tangent of secant inverse? We'll have to do something very similar to what we did before. So let's call that theta. Secant inverse of x is theta. So that tells us that secant of theta is equal to x. So that means if I draw a right triangle, so this angle is theta, secant is hypotenuse over adjacent. So the third side would be square root of x squared minus 1. Tangent of this angle becomes opposite, which is root x squared minus 1 over adjacent. So the answer is root x squared minus 1. Okay, so let's look at the derivative of secant inverse and cosecant inverse. First, let me remind you of the derivative of secant and cosecant, and then we're going to use the formula for derivative of inverse function. Derivative of secant is secant tangent. Derivative of cosecant is negative cosecant cotangent. So to evaluate the derivative of secant inverse, we use 1 over derivative of secant at secant inverse of x. So that would give us secant of secant inverse of x. Secant of secant inverse of x is x. And then tangent of secant inverse of x, which we just evaluated to be root x squared minus 1. So that gives us the derivative of secant inverse is 1 over x root x squared minus 1. We can similarly get the derivative of cosecant inverse, and that would be just negative of the same thing for secant inverse. Let's now do a few examples. So here are 3 examples. Evaluate each integral. So if you look at the first one, if we did not have this expression right here, if it did not have this linear term right here, this would be very similar to integral of 1 over x squared plus 1. So any constant that you have here instead of 1, we can always factor and turn that into 1. But how do we deal with this case when we have a linear term? Well, you can always get rid of linear terms by completing this square. So we're going to go ahead and complete this square. So we have x squared plus 6x. In order to complete this square, we need to divide 6 by 2, which gives us 3, and then square, we get 9. But we need to get to 13, so we need to add 4. So this gives us that. This would be integral from -1 to -5, 1 over x plus 3 squared plus 4. Now, we would like to get 1 instead of 4, so we would like to ideally have 1 here. So we are going to factor 4. We get 4 x squared, or rather x plus 3 squared over 4 plus 1 dx. So this gives us -1 to -5, 1 over 4. So we can put that under square, get x plus 3 squared plus 1. Now this suggests a u substitution for x plus 3 over 2 because that's very similar to tan inverse. So x plus 3 over 2, that gives us du equals 1/2 dx. That means dx is 2 du. Now we have to also change the limits of integration. So I'm going to put the 1/4 here, 1 over u squared plus 1, and then dx is 2 du. Now limits of integral, if x is -1, then u is 1. If x is -5, we plug it in, we get -5 plus 3, that's -2, over 2, that's -1. So this gives us 1/2. I'm combining these two to get 1/2, and then these limits are 1 to -1, tan inverse of u from 1 to -1. That gives us 1/2 tan inverse of -1 minus tan inverse of 1. Now tan inverse of -1 is -pi/4. Tan inverse of 1 is pi/4. And this would give me -pi/4 as the final answer for this part of the problem. Okay, let's look at the next part. The next part is somewhat similar because we have some sort of a quadratic here. This is something squared, and this is kind of a linear term. Again, it's not linear, but there is an exponential squared, and the other one is just exponential. So we can complete this square again to see what we get. So we have integral e to the x over e to the 2x plus 2e to the x plus 2. I'm just copying the problem for now. We are going to complete this square. So the bottom becomes e to the x plus 1 squared. E to the x plus 1 squared is e to the 2x plus 2e to the x plus 1. So we are missing 1 plus 1 here. So this is what we get. Now, if you notice, the derivative of e to the x plus 1 is e to the x, which is up there. So we can use a u sub for e to the x plus 1. So du is going to be e to the x dx. So this portion is in fact du. So this becomes integral du over u squared plus 1. And we just saw that the derivative of the integral of that is tan inverse of u plus c. And eventually we'll have to write down our answer in terms of x. So this would be tan inverse of e to the x plus 1 plus c. So this is the answer to this part of the problem. Okay, so for the next part, we will also have to complete the square again because of the linear term that exists. Let me copy that down. So we have integral 1 over root -x squared plus 4x minus 3 dx. So we're going to complete the square. Okay, we're going to factor a negative sign. We get x squared minus 4x plus 3 dx. So if we complete this square, we are going to get minus, we have x minus 2 squared If we square x minus 2, we get x squared minus 4x plus 4. We are missing a 1 here because we have 3, so we have to subtract 1 here, dx. That would be integral 1 over root. So let's distribute the negative sign. We get negative x minus 2 squared and then plus 1 dx. Now this is very similar to derivative of sine inverse. Derivative of sine inverse was, so sine inverse prime was 1 over root 1 minus x squared. This is 1 minus x minus 2 squared. So that suggests a u substitution for x minus 2. So let's do a u substitution for that. U equals x minus 2. What we get is du equals dx, and that gives us integral 1 over root 1 minus u squared du, and that's just sine inverse of u plus c. And then we're going to substitute that back, so this would be sine inverse of x minus 2 plus c. Okay, next example. So next example is a couple more integrations. The first one is integral of x over x to the fourth plus 1. So we can write this down as x dx over x squared plus 1. So we see that the derivative of this x squared is 2x, which is right here. So that suggests a u substitution for x squared. So u equals x squared, du is 2x dx. Divide by 2, we get 1/2 du is x dx. So we can substitute x dx by du, and the bottom is u squared plus 1. Now we need the limits of integration also. So if x equals 0, u is 0 squared, which is 0. And if x is 1, u is 1 squared, which is also 1. So the limits of integration are still 0 to 1. So this would be tan inverse of u from 0 to 1. Plug in the values, we get tan inverse of 1 minus tan inverse of 0, which gives us pi over 4 minus 0. So the answer to this is in fact pi over 4. Okay, so the next part is somewhat similar, except x is at the bottom. So it looks like maybe that doesn't work because, and by the way, there's a dx missing here, because x is at the bottom, but we can fix that issue. So let's write it down. 1 over x square root of x to the fourth minus 1 dx. Well, we can fix that issue of not having an x at the on top by multiplying it by x. So we get x squared root. I'm going to write the bottom as x squared minus 1. So let's do a u sub for x squared. We get du equals 2x dx. That tells us x dx is equal to 1/2 du. If x is root 2, then u is 2. If x is 2, then u is 4. So we can write this down as the integral from 2 to 4. X dx is 1/2 du over u root u squared minus 1. So this is 1/2. We can take out 1/2, and we know that 1 over u times root u squared minus 1 is the derivative of secant inverse. So this would be secant inverse of u, but we have to evaluate that from 2 to 4. Let's plug in the values. We get 1/2 secant inverse of 4 minus secant inverse of 2. Now, secant inverse of 4 is an angle whose secant is 4 or its cosine is 1/4. So that's not really on the table. So we can't really evaluate that. That would just be secant inverse of 4. But secant inverse of 2, we should know that because that's an angle whose secant is 2 or whose cosine is 1/2. The angle whose cosine is 1/2 is pi over 3. So the answer to this one is, in fact, 1/2 secant inverse of 4 minus pi over 3. So to summarize, we really learned, the main thing that we learned was the derivatives of these trigonometric functions. Derivative of sine inverse is 1 over root 1 minus x squared. Derivative of cosine inverse is negative 1 over root minus 1 minus x squared. Derivative of tan inverse is 1 over 1 plus x squared. Derivative of cotan inverse is negative of 1 over 1 plus x squared. Derivative of secant inverse is 1 over x root x squared minus 1. Derivative of cosecant inverse is negative 1 over x root x squared minus 1. And these three would give us formulas for integral. So integral of 1 over root 1 minus x squared would be sine inverse plus c. Integral of 1 over 1 plus x squared is going to be tan inverse plus c. And integral of 1 over x times root x squared minus 1 is going to be secant inverse plus c. And that brings me to the end of this video. So I will see you in the next video.